Today in lecture 28, we're going to formally introduce the so-called Phasor method, whose real, essentially, with frequency domain analysis is the formal name of the method, but we often call it the Phasor method. And we're going to do a couple examples in essence to establish this. And the next lecture, we will focus on more nodal and mesh examples using the Phasor method. I'll begin by saying the Phasor method is not a method like nodal and mesh analysis. Mesh and nodal are the formal circuit analysis method. In many respects, the Phasor method is an overlay on top of mesh or nodal, if we choose to use nodal or mesh. Okay, so it's not really a method, but it is essentially a way to solve a class of circuit. So we're going to talk about the class of circuit. In last lecture, we began discussing this class of circuits. When we talk about the class of circuits, I'm going to share screen, share the PowerPoint here. We are basically and as we progress, essentially, as we start applying the Phasor method, I'm going to define essentially that class in more formal ways. We are essentially looking at circuits that have these sorts of functions as sources. In other words, all the independent current and voltage sources will be of that nomenclature. All right, they will be of sinusoidal form with a particular wave amplitude. In this particular case, I'm showing you a voltage function, but it could also be a current function. It has a radial frequency in radian per second, that's omega here, and some phase shift. So this is as general as it gets. If you wonder, this class of circuit is the same class of circuits that your home electrical outlet falls under. This is what we call sinusoidal circuits, where you have these signals as sources. In the case of your home, when we talk about 60 hertz, the frequency 60 hertz is omega divided by 2 pi. So omega is what's called the radial frequency in radians per second, and the frequency in hertz is the radial frequency divided by 2 pi. So for the home, for home signals, it would be 2 pi times 60 hertz would be omega in this sense, okay, which would be about 377 radians per second. So we're looking at these types of signals, how to use phasors for these types of signals operating in our circuits as sources, okay? So the entire phasor representation is based on Euler's identity, which is given right here. Euler's identity tells us that e to the j theta is equal to cosine theta plus j sine theta, okay? So when we look at a function like this, and this would be the type of functions that are going to be in our sources here, we say that that function, because of Euler's identity, is equal to the real part being just the cosine part, the real part of Vm e to the j omega t e to the j phi. Okay, so we're going to, and then you're going to bear with me for a little bit. I'll explain a little bit why this is the case, why we do this. I know this is not making that case yet, but I will. I promise I will. We're going to say that Vm e to the j phi, often we will express that as Vm bracket phi, is equal to the phasor representation of the original function. Okay, now keep in mind that this particular term, e to the j omega t, is always there. So we actually don't show it, but in many respects, it is there in the phasor representation as well. But because it's there every time, is there everywhere, we don't show it. It's omnipresent. Okay, so I'm going to show you that. So for the time being here, we're going to say that this written as either as Vm e to the j phi or as Vm bracket phi. This implies this is the same thing. We're going to say we'll define it as the phasor representation of V of t. Okay. All right. So here's the phasor method in a nutshell, and then we'll go and try to give more support for why this is the case. The typical circuits we're going to have are circuits with resistors, inductors, capacitance, and dependent sources as well, okay? And we have sources, and you can see that I'm not showing either current or voltage. We're going to have sources that look like this, many sources, okay? So we're going to say that when we have sources that look like this, the response, and the response can be either voltage or current. I'm showing you voltage here. The response is going to be, so if you have a source that has an amplitude A cosine omega t plus phi, the response is going to be B cosine omega t plus theta. And we kind of had that sense when we solved the example problem using differential equation for the right-hand side being a cosine function. Okay, so if we have a cosine function on the right-hand side or a sine, we're going to have a cosine function essentially as a response. So we say that, all right? And we say that in steady state. So when we say steady state, we're saying that the natural response has died. These are circuits that are on for a fairly long time, at least seconds. It doesn't have to be long for the natural response to die, at least seconds, so that the natural response, the exponentially dying part of the response has died. All we have left is the forced response, is the particular response, which we now call the steady state response. Okay, that's what we're looking at in these circuits, because that's the class of circuits we are concerned with. All right, so instead of solving this problem here, because this problem would require a differential equation solution, just like we did before, we are going to solve this. We are going to replace the sources with their phasor representation. Okay, remember that I said the e to the j omega t part is always there, even though we're not showing it in the phasor, it's assumed present. So we're going to solve these with the sources being converted to their phasor representation. Okay, when we do that, we can show that the result is equal to the same b as in the previous example, and the same theta, but with that exponent form in terms of function. So we get the same two unknown. Okay, and that's the magic of the phasor. And I'm going to show you a little example that essentially shows that. So in one page, let's look at what that means. That means this is the original circuit that you're going to be given. And you're going to be given a circuit in which you're going to be asked to either calculate voltage, current, node voltage, mesh currents, or that we're going to some sort of circuit analysis problem. We are instead going to convert that circuit to what we call its phasor representation, which is converting the sources to these essentially phasor form sources. Okay, and in doing so, the original problem is this. We get this. Okay, so the original problem is on the left, but what we'll be solving is on the right, and it's a lot easier to solve the problem on the right. Okay, and we are going to be able to solve the problem on the right by not using differential equations. And that's a really nice thing that the phasor method is going to give us here. So, but we get the same magnitude b and the same angle theta using this function that we needed in the original problem. Okay, so we're going to practice this, and we'll try to make a case for this in a little bit. So let me try to make a case for this with this simple example here. We have an inductor. It's, I'm picking up with 2 Henry inductor. And what are we saying here? We're saying, okay, the inductor it's connected in a circuit, and it has some current, the current. So I want you to calculate the voltage across the inductor for 2 currents. The first current is 3 cosine 5t plus 40 degrees. And the second current is its phasor representation. And I want you to see how that gives you the original essentially problems, the unknowns we need in the original problem. So we're going to do it for 2 current. The first current is, again, the cosine, 3 cosine 5t plus 40. Then we're going to do it again using 3 e to the j5t plus 40 degrees and see how that plays out in terms of the circuit here. And that will kind of really a little bit formalize the phasor method for us. So I'm going to go to document camera to do this with you here. Okay, so I've written the problem here. So this is not a complicated problem. All I'm asking essentially is for you to apply essentially V is L di dt. That is all I'm asking to apply here. So this is not a trick question. This is not a complicated problem either. This is just saying, given this current, okay, what's interesting, essentially, this is the phasor representation. Okay, this is the phasor representation of the cosine. So you'll see the benefit of having this. So let's look at, again, let's look at case one. So case one, what do we have here? What do we have here if we differentiate here? We have a 2 Henry inductor, so we get 6, okay, times 5 minus sine 5t, or multiply, obviously, sine 5t plus 40 degrees. Okay, that's what we have. So what do we got here? We got minus 30 sine 5t plus 40 degrees. Okay, so that's what we have here. All right, so we're going to do two things to put things in context here. The Phasor method is really in relationship to the cosine function, not the sine. So I'm going to convert that sine to a cosine, and I can do that by subtracting 90 degrees to the angle. So it's minus 30 cosine 5t plus 40 degrees minus 90. So which is minus 30 degrees, minus 30 cosine 5t minus 50 degrees, okay? The other thing I'm going to do, I'm going to subsume the minus sign here by adding 180 degree in angle so that I can get rid of the minus sign as well. So this is essentially 30 cosine 5t minus 50 degrees plus 180. The minus sign is subsumed by adding 180 in the phase. So what does that give me? That gives me 30 cosine 5t plus 130. Okay, so this is v of t for the cosine, using the cosine function. Okay, so I'm going to over here do case number 2 here. All right, so that's what we got. So let's use this for case number 2 here. Okay, so v is equal to, again, L di dt. So I get the L is 2 Henry times 3, and essentially derivative of this. So what do we get here? The derivative get us J5, and then e to the J 5t plus 40 degrees, and that's V. Okay, essentially I'm just doing L di dt on this function here. So multiply 2 times 3, and then the J5 comes, taking the derivative of the exponent here, and then that. Okay, so let's collect some term here. 6, that's J30, e to the J5t, e to the J 40 degrees. How's that? Okay, so that's my voltage V of t here for that function here. All right, so let's do a little bit more manipulation here. You can recall again the complex number J. We can write it as 1 e to the J 90 degrees. Okay, again, if you remember this in terms of complex number, this is a real and imaginary. The complex number J is this number here. Okay, 1. So we can, in polar form, we can write it as 90 degrees at a magnitude of 1. Okay, that's what we have here. So this is converting the complex number J from rectangular to J in polar form. J in polar form is 1 at an angle 90. Okay, so if I do that, then the voltage V of t, in this case here, is 30 e to the J5t, e to the J 40 degrees, e to the J 90 degrees. Okay, that's what we got. Again, what do I have? If I combine things, I have 30 e to the J 5t plus 130 degrees. So compare these two. I get the 30. I get the magnitude I need. Okay. I also get the phase. I get the phase I need. Okay. So I get the same two values that I need in the original problem using this. Okay. What essentially you're going to find out when we do this, solving this problem here gives us exactly the same answer, but it's a lot easier because When we differentiate an exponent, we get the same function back. So whereas when we differentiate essentially a cosine function, we get a sine function, essentially we get a different function, we get a sine back. So the ability for the exponent to be differentiated and give it back to you, it makes it a lot easier to solve problem that involves inductor, capacitor, essentially when they're excited by sinusoidal sources. So this is essentially the basis here. This is going to be easier. This won't require solving differential equations, whereas this particular does. So we're going to formally define the Phasor method here, and then we'll look at an example and we'll write the rules for under what case can we apply the Phasor method. So in order for us to define the Phasor approach, the Phasor method that we're going to overlay on top of mesh and nodal, we're going to look at how we treat resistors, how we treat capacitors. Start by the easiest case, the resistor. So we say if we have a resistor and we put a current given by AM, with an amplitude AM with an angle theta. Remember when we write that current like this, it's really AM e to the j omega t e to the j theta. The e to the j omega t doesn't show, but it's omnipresent. Okay, so when we write this, that's what this means here. All right, so one thing we're going to see here, when we apply the Phasor representation, we're going to try to use capital letter to indicate the difference between the Phasor representation and the original function, which will be in lowercase. So when you see capital letter, that means the Phasor representation of the function here. So of course, if we have this as a current, then we can essentially apply Ohm's law. And we say that Ohm's law, the voltage, again, capital V, the Phasor voltage is resistance times the current. So it's RAM at an angle theta. We're going to define now the ratio of the Phasor voltage to the Phasor current as the impedance. Of course, for the resistor, the impedance is the resistance of the resistor, so it's the same. But you're going to see the difference when we do inductors and capacitors very shortly. So for the resistor, the impedance of the resistor is the resistance. And so there's not a whole lot that has changed here. But let's look at for the inductor. And this is the example that I just did on paper here, if you will. If we put a current that's given, a Phasor current that's given by an amplitude and a phase angle theta, and we say what is the voltage, the Phasor voltage, again, we L d I dt. So we can show that the Phasor voltage is given by j omega times the inductance of the inductor times the current. So this is the power of the Phasor method right here. That actually shows you that. It shows you that the relationship, if you apply a Phasor current to an inductor, the relationship between voltage and current in Phasor, that's what you see them in Phasor, it's a scalar. It's not a derivative, it's j, the complex number j, times omega, the frequency of the source, times the inductance of the inductor times the Phasor current. So it's almost like we have a complex resistor. Inductors are not resistors, all right? But the relationship between the Phasor current and the Phasor voltage is a scalar relationship. Phasor voltage is equal to J times omega times L times the Phasor current. That's going to be powerful in helping us solve circuit with inductors without the use of differential equations. Okay, that's the reason why we do this conversion to the Phasor format. So a little bit more here. So we will define the impedance of the inductor as J times omega times L. And we can show that the voltage leads the current by 90 degrees because the complex number J is going to introduce a 90-degree phase shift into essentially the voltage. So the voltage is going to be ahead. It's going to lead the current by 90 degrees. Okay. So again, I'm going to put that all into an example. We're going to do a lot more example to formalize this. I know this is a little bit confusing right now. You're not seeing that. But for the inductor, again, when we excite an inductor, just like we did on paper a little bit ago, by a Phasor current, then we can show that the Phasor voltage is J, the complex number J, times the frequency omega, times the inductor's inductance, times the Phasor current. That is essentially the impedance of the inductor times the Phasor current. That's pretty powerful. And that's going to be pretty useful to help us solve this circuit. All right. So we see that. Let's look at the capacitor. So the capacitor, if we put a current, a phasor current with an amplitude AM and a phase angle theta, so we can show that the phasor voltage is the impedance of the capacitor. And the impedance of the capacitor, it's 1 divided by J, divided by omega, divided by C. Okay? So it is the impedance of the capacitor is going to be that. Okay, 1 divided by the entire quantity J omega C. All right. So, and I'm going to talk a little bit about, capacitor impedance and so forth in a little bit. All right. So we can show that the voltage for a capacitor lags because of the J being in the denominator. If we move J on the numerator, it's going to be minus J. It lags the current by 90 degrees. Okay. So for these elements, which are going to be which are the 3 elements we concern, the 3 passive elements, in phasor, if we convert the circuit, and convert the circuit meaning convert all the sources to phasors, and we have 1 frequency, that's going to be one of the requirements. Then for this element, voltage is equal to impedance times current, where for the resistor, the impedance is the resistance, just like before. For the capacitor, the impedance is 1 divided by quantity, J times omega times C. And for the inductor is J times omega times L. Okay. When we do that and we're operating in the phasor domain, if you will, then we can actually use the same method we use in the first month and a half as if we had complex resistors. They're not resistors, only resistors are resistors, but the inductors and the capacitors behave in the way we treat them if we are using phasors, if that's warranted. So we have to first make sure that's the case. We can use these impedances for these resistors, for the capacitor and inductor, just like we do for resistor. So we're going to start some examples. So again, let's look at this case. This is a case we did using differential equations. We did this case using differential equation. So first thing I want to say when we're looking at this case here, I want to define under what case can we use phasor? Can we use the phasor method, the phasor approach? We're looking at circuits that have sinusoidal signals only. And by sinusoidal signal, I mean cosines and sine. The circuit must have 1 frequency. In this case here, the frequency is 2 radian. You can have multiple sources, but they all need to have that 1 frequency. Okay? So in this case, it's going to be 2 radians per second. All right? Also, these circuits are considered on for a long time. There is no switches turning off and on. You can see the circuit essentially is operating for a long time. So the natural response has died out. This is what we call the steady state response of the circuit. Steady state means that it's reached a steady state. It's on at least a few seconds so that the natural response has died out. Okay. And the steady state, in essence, is the forced response. It's what you used to call the particular response in the circuit. Okay. So this is the standard. I mean, of course, this is a 1 loop, 1 mesh circuit, but yet it will show us how to use the phasor method in that 1 mesh circuit. Okay. So let's talk about how we do this. The first thing we do, we convert all sources and all inductors and all capacitors to their phasor form. Okay. The source is essentially, again, this is a source that has an amplitude 4. The frequency is 2 radians per second, and it has 0 phase angle. Okay. All right. So the phasor is going to be 4 at an angle 0. That's what you got here. Then we calculate the impedance of each inductor using the impedance formula J times omega times L, with omega being 2 radians per second. Okay. For the capacitor, we calculate the impedance for each capacitor using the formula 1 divided by J omega times C. Okay. So that's converting the circuit to phasor form. When we do that, that's what we get. We get the phasor form of the voltage. We get the inductor with its impedance, J10, and we get the capacitor with its impedance minus J25. So one thing we're going to talk about here, inductors always have positive imaginary impedance. that flows from the impedance calculation, which is J times omega times L. For the capacitor, the impedance for a capacitor is 1 divided by J omega C. You can actually move the J to the numerator, so there will be minus J divided by omega C. So the capacitor impedance is always negative, imaginary, just as a check for you here. Once we convert the circuit to phasor, we can use it as if we're talking about complex resistors. They're not resistors, but we can use them. We can actually combine these things. We can combine the impedance like we were combining resistors in the past. So in this particular case here, the voltage 4, again, 4 at an angle 0 is 4, is equal to the current, the phasor current I, times the sum of the impedances. Again, I can combine impedance just like I combine resistor in series here. So you have 4 plus J10 minus J25. Okay. At this point, this essentially, I'm going to calculate the current I, and then I'm going to calculate VC and VL and whatever I need to calculate. Okay. So this becomes a complex arithmetic problem pretty quickly. This is where I need you to be using your calculator. So I don't expect you to do these things by hand, but just so that we can. So I then becomes 4 divided by 4 minus J15. Here I'm showing to you how I convert the 4 minus J15 to polar form. From my own perspective, you need to be able to plug this thing into a calculator and give me the current I. Okay. Generally, you have to be able to give me the value of the solution in either polar form, usually in polar form, but also in rectangular form. Okay. So here I'm converting to polar form just to show you how you would do this if you had no calculator that can handle complex arithmetic. And then from then on, I can do the division easier with polar form in the denominator. So this is the current, magnitude, and phase. Okay. Again, that's going to take you some doing to kind of get comfortable with doing these complex arithmetic. All right. Once we get the current, then I can calculate the capacitor voltage, which is the impedance times the current. All right. That's the magic of the phasor approach. It allows us to treat capacitor essentially as a complex resistor, if you will. It's not a resistor, but as a complex resistor where the voltage in phasor is equal to the impedance of the capacitor times the phasor current. So once we have the current, we can multiply by the impedance of the capacitor. And again, I can do the multiplication by converting each part to polar form. I expect you to use your calculator to do that, not to do all this conversion. And then we find the capacitor voltage in polar form. All right. So that's the solution of the circuit in phasor form. Now we have to go back to the original problem, but we have the two parts that we needed. We have the angle, we have the magnitude and the angle. So just showing you the phasor representation of these things, just to show you. But the final solution, the phasor problem we solve is given by this. The original problem is 6.45 cosine 2t minus 14.9, that phase angle we got. Okay. This is the essence of the phasor method applied to a one loop problem here that we do, but we're going to use it in the future, essentially in the next lecture, to do full-on mesh, nodal, and then eventually Thevenin, Norton, and eventually we're going to do power as well. Okay, so I hope that gives you a good introduction to this. So let me recap before we go. Okay, I'm going to go to the document camera here, and then I'm going to recap, and then we will pick up the next lecture here. So, two things I'm going to say. First, when do we use the phasor approach? Okay. So, phasor approach, A, all sources are sinusoidal. For example, All sources are of this type. Okay? Whether it's whether current sources or voltage sources, they're of that form. Okay? So all sources are sinusoidal in nature. Okay? B, the circuit has a single frequency omega. Okay? Single frequency omega. All right? So, for example, so omega here is 6 radians per second. Okay? So the circuit has one single frequency. So you can have multiple sources, but they all need to have the same frequency in order for you to use the phasor method. Okay? Okay. C, these sources are on for a long time. Long enough for the natural response, what we used to call the complementary response, to go to 0. Okay? And this is what we are left with the forced, what we used to call particular response, which we call the steady state response. Okay? All right. So in essence, I'm laying the groundwork. When can we apply the phasor approach? Okay. So we're talking about a single frequency in the circuit. All sources are sinusoidal in nature. You can have multiple sources, but they all need to have a single frequency. I'm showing you that here. And these sources are long enough, are on long enough here. Second question here. How do we convert the circuit to phasor domain? Okay, that's the second fundamental question here. And once we do that, then we can do mesh nodal voltage current division, just like we did in the past, without having to solve differential equation. So A, convert each source, and I'm talking independent source. We don't, dependent source stays the same. To its phasor form. Okay, form. All right, so what I'm talking about here, if you have a source that is 3 cosine 5t plus 25 degrees, we converted, that becomes 3 at an angle 25 degrees, which really means 3 e to the j 5t e to the j 25 degrees. So when we write this, that's what this means. This is the phasor representation of this. Okay, if we have a sine, 6 sine 4t minus 20 degrees, we first have to convert it to a cosine. So this becomes 6 cosine 4t minus 20 degrees minus 90 degrees. Okay, so this is 6 cosine 4t minus 110 degrees. And then we convert this to this phasor. Essentially, this becomes 6 at an angle minus 110 degrees. Okay? So we convert each source to its phasor form, to its phasor representation. So I'm giving you some example of that. And then B, calculate each inductor impedance with Z equal J times omega times L. Of course, again, note the frequency of the source. Okay. So we calculate the impedance of each inductor. We calculate the impedance of each capacitor. Of each capacitor. 1 divided by J omega C, which we can also write, by the way, as minus J divided by omega C, because 1 over J is minus J. Okay? Once we do that, then we can proceed to solve the circuit just like we had complex resistors, just like we did in the first month and a half. We're going to pick it up using mesh, nodal, and other types of method in the next lecture. Okay.